like we are using any system, okay, not a single component. If we are talking about any system we are taking, so there are the reason to calculate the magnitude response, frequency response, and phase response is, first of all, we have to identify, like this is my system. Have to identify two things. One is the system is stable or not. Okay. Second thing is that if system is stable, what is system response with respect to frequency? Okay, so we require two things. One is the system is stable or not, and if system is stable, then what is the response with respect to frequency? Okay, either the system response is constant. Second thing, it will be change with frequency. Okay, so generally thing is that if I am taking any system, the system response is not constant. We are considering that case is only a ideal case. Why system response is not constant? Because system is designed with the help of components. Like you design an amplifier. Okay, amplifier requires some operation. Amplifier, basically amplifier, if you design either with the help of BJT, with the help of resistors, so every component is frequency dependent. If you increase the frequency, the response will be changed. Okay, if you increase the frequency, the response will be changed. If first thing is that what happen if we increase the frequency or if we vary the frequency. So if you increase the frequency, the electrons vibration is increased. Okay, and due to this vibration, the response will be changed. If I say the resistance, now if we increase the frequency, the resistance value will be changed. Why? Because the electron vibration started. Electron vibration in its exact position. So that will be increase the resistance. So if you have a design a resistance that it will be a 10 kilo ohm, if you increase the frequency, it will be showing the response different. Okay, if you increase the frequency in a gigahertz, that particularly resistance will not be suitable. Why? Because that will be operable only on a kilohertz range, but you are providing the megahertz, gigahertz. Okay, so system response is not constant with frequency. If we are considering the system response is constant with frequency, that is only for the ideal case. So that means every response is changed. Okay, saw that if I am talking about the ideal op amp, the gain AS is simply A. Okay, that is either minus RF by R1 or 1 plus RF by R1. Okay, and in both cases it is constant because RF is constant, R1 is constant. That means AS is constant. A is constant. Generally, I am taking the A because it is not a function of omega. So that's why I am taking it is a constant gain, no change. But if we are talking about the practical op-amp, this A of S is omega U by S. Okay, that is dependent on frequency. Omega U by j omega. S is equal to j omega. So if you change the frequency, increase the frequency, AS will decrease. If decrease the frequency, AS will be increased. So for every system, one important parameter is the gain bandwidth. GBP. gain bandwidth product. That means the gain multiplied by the bandwidth is always a constant. If you increase the gain, bandwidth decrease. If you decrease the gain, bandwidth increase. Okay, increase the gain, bandwidth decrease, decrease the gain, bandwidth. So their multiplication factor should be always a constant. Okay, so that's why the system response we have to calculate, and that particularly will be calculated using the frequency response. Now second thing is that how to identify the system is stable or not. So for this one we require a magnitude response and phase response. Okay, you will discuss that thing in more detail in the control system. The topic is the Bode plot. Okay, the magnitude response and phase response will give us two different parameters. One is the gain margin and phase margin. Okay, and on the basis of this one, we identify my system is stable or system unstable. Okay, so we calculate a magnitude, phase response, and the frequency response. That's why it is important. Any doubt?
Clear, sir.
Clear? Fine?
Yes. Fine, sir.
Okay. Any other points? Yes, any other doubt? I think you discussed the Bode plot also in the EEC little bit.
Yes, sir.
So that condition we use for to calculate the system stability, and how we calculate the Bode basically phase margin and gain margin with the help of magnitude response and frequency.
Clear, sir. No.
So, we are talking about the stability criteria. So I think the stability when gain margin GM is greater than 0 dB. Okay, and phase margin TM will be greater than 0 dB. Okay, and unstable when GM less than 0 dB and PM less than 0 dB. Okay, any other doubt? Yes, any other doubt? Any other
Sir,
topic?
sir, in
Yeah.
body plot, we find poles and zeros, sir. The
Yeah,
poles
with the
means
help of pole zeros, we calculate the phase plot and gain plot.
Sir, the poles means the output of the system is goes to infinite.
Yeah, you are saying that. Just wait a minute. I just use headphones. I am not audible to you properly. Just give me a minute. Yes. Now tell me what you are asking. Yeah.
Sir, poles means the output of the system is goes to infinite.
Yeah. Where the basically the position where the system will be goes to infinite.
Okay, sir.
Okay. We have a like for example we have a equation uh, a of s is equal to n of s upon p of s. Okay, so n of s gives us the zeros. If I put n of s is equal to 0, that will be gives us the zeros. And if I put the p of s is equal to 0, that gives us the poles. Okay, so if p of s is equal to 0, if this term is 0, so that means a of s is equal to infinite. So where the system will be go up to the infinity, that particularly position is called the poles. Okay.
Okay, sir. Clear, sir.
Any other point? Any other topic?
Sir, op-amp transfer function and that is single stage amplifier, that is stability of single stage amplifier.
Okay. That is the week 5, I think so.
No, sir, in week 7.
Stability of single state.
That is, sir, lecture 5.
Lecture 5. Can you tell me the name? I don't know the name of that one.
Single stage amplifier stability.
Okay.
Week 7, lecture 5.
Okay, no problem with that. Single stage amplifier stability. So first of all, we have
Yes, sir.
designed. We can design a single stage and multi-stage amplifier. Okay. So how we find out the stability? So first of all, if we are talking about the stability system, so if you remember in the Laplace domain, I think you remember that a system is stable when they have poles must lie in left hand side of S plane. Basically, in the signal system, you for the stability you discuss something different. The difference is that in the signal system, a system is stable if ROC contain j omega axis. You
Yes, sir.
remember that?
Yes, sir.
Okay. If we are talking about the left-handed signal, my signal should be left-handed signal, so poles will be like in that way. Okay, my ROC will be this one. Okay, and toward the left side. Okay, that will be contain the j omega axis.
Yes, sir.
So I can say my system is stable. Okay, or I use this type where this is the ROC and my signal is the right sided signal. So again, that contain the j omega axis. So again stable. Or third case is you have a two poles, one in this side, one in this side. This particularly pole will be the right side. Okay, this pole will be left side. Okay, so ROC is this part. This is my ROC. This is my ROC. And that also contain the j omega axis. So I can say my system is stable. Okay, but
Yes.
when we are talking about the electronics part, okay, so in the case we just discussed that u of minus t is one signal, that is the left sided signal. Okay, if this is the t is equal to 0, then u of minus t will be present at t is equal to minus 1, minus 2, minus 3, okay, and so on. But if we go with the electronics part, so when we start our circuit, when we start working our circuit, my circuit will be giving the response. If I am not applying any voltage to any of the BJT, before that, how can I consider that particularly BJT will be working? Okay, so that means if at t is equal to 0, I apply the signal on any diode, any BJT, any resistor, any op amp, after that my system will be working. So that means response will always be the right side. It is not possible in the analog circuit, in the case of analog part, circuit part, that if we apply a signal before that we are getting the response. Okay, a simple example is that when you switch on the electricity, the light will be glow. If you are not switching on the electricity, how can you consider that before that light will be glow? Is it not possible? Okay, so for the understanding of signal system, that is fine that signal should be the left-sided signal. But for the electronics part, it is not possible that signal should be left-sided signal. If we on the switch, the light will be glow, the fan will be working. So always after applying the signal, my circuit will be working. So that means at t is equal to 0, I apply the signal and after that it will be start working. So that case is not acceptable for a electronics. Okay, and if that is not acceptable, that means this case is not possible and this case is not possible. Only one case is possible for the electronics. Clear?
Yes, sir.
Now for the stability of electronic system, for the stability of electronic system, we require that poles will be left hand side, because the signal should be poles will be left hand side of SPM. Okay, now how much stable? That is depend as how much far from j omega axis. Okay, if it is moving like we have a one pole here, my system is stable. Okay, if I shift my pole towards this point to this point, my system will be now marginally stable. Okay, fine. So this is the stability part. Now if we go with the amplifier will be designed with the help of feedback circuit. Okay, now overall what is the gain? V naught upon Vi is simply Ai upon 1 plus Ai beta. Okay, now what is Ai? That is omega u by s, because the system is now non-ideal system. Operation amplifier is not a ideal option. Okay, so that will be dependent on the some frequency component. So Ai is nothing but omega u by s. So if we put a omega u by s, so V naught upon Vi is omega u by s into 1 plus omega u by s times beta. Okay, so that is omega u by s upon 1 plus omega u s by beta. That is omega u by s. Okay, if we are talking about the so loop gain is what? This is Ai, this is beta, V naught Vi. Okay, this is a loop gain. This one is the loop gain. So it is a Ai times beta.
Sir, loop gain function of single stage is A1F divided by 1 plus S by omega 1.
Okay. No, actually, I am just talking the. Okay, you are taking the feedback path. Okay, 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 okay.
Yeah, yeah.
If I am taking only the operation amplifier, not a single stage amplifier, I am just taking the operation amplifier right now.
Okay, okay,
Okay.
okay, okay.
If we are
Okay.
taking the single stage amplifier, then a loop gain is Ai times beta upon 1 plus S by omega. Okay, that is for the single stage amplifier. I am talking about the operation amplifier only. Okay, so we can take this one if we are talking about the single stage amplifier. This is a single stage amplifier. So for that one, the loop gain is Ai time beta upon 1 plus S upon omega u. Okay, and if this is the loop gain, what is the closed loop gain? Closed loop gain, simply that is Ai upon 1 plus Ai beta. Okay, I multiply with beta 1 upon beta, and this Ai beta is a basically loop gain in a feedback system. Okay, in a feedback system, this Ai beta is the loop gain. Now for the single stage amplifier, this AI beta is equal to AI beta upon 1 plus S upon omega u. This is loop gain for feedback circuit. And this one is the loop gain for single stage amplifier. Okay.
Yes, sir. Now I understand. In the lecture, professor used 1 by f into AIF, that is total function 1 plus loop gain function divided by 1 plus loop gain function.
Okay.
Uh, the closed loop transfer function is equal to 1 dot loop gain function divided by 1 plus loop gain function. These
Okay.
terms is um, little bit confused
Now it
me.
is clear.
Yes, sir. Now it
We
is
we
clear.
have if we are talking about the normally feedback system, this feedback system. So what is V naught upon Vi? Simply V naught upon Vi is AI upon 1 plus AI beta. We already solved this one in the week 1.
Yes, 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 sir.
Okay. Now if I multiply it here by beta and divide it by beta. Okay. So this AI beta is the loop gain. That means this is a loop created. Okay. If you see that this AI, the signal will be feed with beta. Again, it will be go to AA. So this is the loop gain. Okay. This factor is the loop gain. So what should I do? I just return as a AI beta as a loop gain. So it is a loop gain upon 1 plus loop gain into 1 upon beta. This is a
Yes,
simple feedback
yeah.
system. Okay. Now, if I am going with the single stage amplifier, so in the case of single stage amplifier, what happens? Here the loop gain is not a AI beta. This is the AI beta upon 1 plus S upon omega. So now I put the value of this loop gain into this function. So we are getting the V naught upon Vi is equal to AI beta upon 1 plus S upon omega u. This is for the numerator, and for the denominator 1 plus AI beta upon 1 plus S upon omega u, okay, times 1 upon beta. Okay.
Yes, sir. Yes, sir.
And now if I divide with the AI beta or with this one, or I can simplify that one also. Okay, if I take a common loop gain from the denominator, loop gain from here, so both will be cancelled out. So 1 upon 1 plus 1 upon loop gain multiplied by 1 by beta. Okay,
Yes.
from this
This
one I
is
can directly
this is
write
closed loop transfer function.
for singles for the single stage.
Yeah, yes, yes, for the single system,
Okay.
single state. Yes.
Now loop gain, put the
Now
value
it
of
is
loop
clear
gain. So
to
it
me.
is a 1 upon 1 plus 1 upon AI beta upon 1 plus S upon omega u times 1 by beta. Now can take a basically LCM and just solve it. So you will
Yes, sir.
get the equation is 1 over AI beta upon 1 plus S upon omega u plus 1. AI beta upon 1 plus S upon omega u. Again, if we solve it, 1 upon 1 plus AI beta plus S upon omega u whole divided by AI beta upon 1 plus S upon omega u. Okay, it is in multiply. I can take into the divide. Okay, so into, sorry, 1 upon beta is also there. 1 upon beta. Okay, so this term is in, I can take multiply. It is a 1 plus AI beta plus S upon omega u times 1 plus S upon omega u divided by AI beta and whole multiply with by beta. Okay, so this beta and beta cancel out. So I think we have equation of 1 upon AI plus beta plus S upon omega u times AI multiply 1 plus S upon. Okay. Yes, any doubt?
No, sir.
Any other topic? Yes, Soma. Next topic.
Sir, then what will be the Bode plot for that in single stage?
Border plot. Okay.
Yes, sir.
So you got the transfer function. What is your transfer function you are getting? So V naught upon Vi is I think somehow it is 1 by F into 1 upon 1 plus S upon A naught F omega u. Okay, we consider the A naught F
Yes,
should be greater than 1. F or beta basically.
yes, sir.
Okay, we are getting this is the border. This is a basically transfer function. Now, first of all, we find the location. Okay, so if you consider that one, so zeros, if you identify the zeros, so no zero. Because in the numerator, there is no particular
Yes,
term in the
yes,
form
sir.
of s. That means there is no zero.
Yes,
Second,
sir.
we consider the pole. So how we get the pole? We just equate the denominator term equal to 0.
Yes,
So
sir.
1 plus s upon a naught beta omega u is equal to 0. So minus 1 is equal to s upon a naught beta omega u. That implies s is equal to minus a naught beta omega u. That means this is the position of pole.
Yes, sir.
Okay. Now it is a negative term. So it will be anywhere in the left hand plane. So that is a naught beta omega u, the position of pole, one pole that is exists and that will be available in the left hand side of
Left hand side.
S plane. Okay, so
Yes, sir.
it is stable. But the thing is that is it stable for all values? Of a naught beta and omega u. Okay, because we have two terms, one is the loop gain and one is the basically bandwidth,
Yes, sir.
open loop bandwidth. Okay, because if you consider the of this is the gain of this is the gain of op amp. Okay,
Yes, sir.
this omega u is what? It is the open loop bandwidth. Okay, why it is called the open loop bandwidth? Because if you plot the response of this one, so when s is 0 it will be up to infinite, when s is increases it will be down. Okay, when s
Yes,
is
sir.
omega u, the ai will be 1. When s is equal to omega u, this become a 1, and because of this one my magnitude will be 1 by root 2. If you calculate the transfer function, and after calculating the transfer function if you calculate the magnitude, so because of this one you will be getting the magnitude will be 1, because it is a upon
The
1
hardware
plus
root.
omega u by s. So, sorry, s by omega u. Yeah, we are getting this one now. S by, yeah, this one.
Yes, sir. Yes, by one.
Okay. So when s is equal to omega u, so it will be 1. Okay, and if we take the magnitude, so ai upon 1 plus j into 1. If we take the magnitude, so it is ai upon root 2. So
Yes,
your
sir. One by
magnitude will be 1 upon root 2 at s is equal to omega u. So that's why it is called the open loop bandwidth. Okay. Now
oh,
there are two parameters where the on this one the stability will be defined. One is the a naught beta, that is the loop gain, and second is the open loop bandwidth. Okay. So I already tell you that if it is far away from the j omega axis, that means if this distance is high, we can say it is a stable. But if distance reduces or less, it may be move up to the marginally stable. Okay, so it will be stable to go marginally stable. Okay, it will not be unstable, but it will be go stable to the marginally stable. Why it will be not going to the marginally stable? Because a naught b, that is the loop gain, positive, and omega u bandwidth, that is also positive. So both parameter will be positive, that means it always will be the negative or it will be equal to the 0.
0. Yes, sir.
If it is negative, we can say it is stable. If we go to the 0, we can say it is a marginally stable, or maybe marginally stable. After that other parameter we can say it is a stable or unstable. That means it will be contain both condition, stable or unstable. But that will not be a positive value, so we can't directly say it is a unstable. Okay.
Yes, sir.
Now, now the two things. One is the AIF. There are some limitation in AI beta. There is some limitation. So it will not, should not high enough. Okay, should not high enough. Why? Because if AI beta will be high, your transfer function loop gain, that is AI beta upon 1 plus s upon omega u. So that will be high. Okay. Now the second thing is your omega u. Okay. If you increase the omega u, the condition is that okay, if you increase the omega u, the thing is that your lobe gain will be reducing. Okay. And if you increase omega that you take greater than omega u, so your loop gain is AI beta. This component is greater than 1, so I just neglect the 1, so it is directly I can write as a s upon omega u. Okay, so it is AI beta into omega u divided by s. Okay,
Yes, sir.
what is your unity gain frequency? Okay, that means your unity gain frequency is what? Your loop gain will be 1.
Yes, sir.
Okay, unity gain frequency of loop gain. So that will be 1. So S is AI beta times omega u, or we can say the omega is AI beta times omega u. That is also very high. Okay, so it is simply dependent on stability, is simply dependent on your omega u. Understood?
Yes, sir.
It is not dependent on AI beta, it is only dependent on omega u. If
Omega
your
u.
omega u will be higher or lower on the basis of you can define the system stability is better or worst. Next topic. Should I draw the border plot of this one also?
Now I understand that will be in A1 FW, that is omega u, will be the unity gain
Mm-hmm.
frequency.
Yes.
And in 3 dB,
Mm.
then 3 dB bandwidth, loop gain will be omega u.
Yes, omega u.
Okay.
Okay, sir.
Any other topic? We calculate the Bode plot for find the exact stability criteria. What value we should consider of omega u, so the system Bode plot will be basically it will be providing me the stable system. Okay, so for that particularly purpose we are calculating the Bode plot.
Sir, it is
Yeah.
compulsory to follow the Bode plot of third order forward amplifier. That will be last two lectures are something little tough for me. That
Okay.
is lecture 9.
No, you can check that when we are not going little bit much far in details. That is because generally what we are doing, we are taking the first and second order.
Yeah, yeah, yeah.
Okay. Third order generally what we consider if we increase the orders, automatically system will be go up to the instability. Okay.
Yes, sir.
First order
Then
system is
we have to convert it in first order.
hmm,
Then it will be operate.
first order or second order maybe.
Yeah, yeah, yeah. First order
Okay,
or
of course.
second order.
Because if we increase the order, automatically the system will be go up to the instability. Okay, it
Yes,
will
sir.
be reached to the unstable. First order system is more stable. Second order system less stable as compared to the first order. Okay.
Yes, sir.
Sometimes it is a marginally stable or it is a very less stable. But third order system, if we go, the chances is either this one will be the stable, this will be the marginally stable, or maybe the unstable also.
Yes, sir.
Any other topic? Yes, Karthik, if you want to ask any other any topic. Okay, yes, Soma.
No, now it is clear, sir. That is uh,
Okay. Your deadline of week 7 is
12.
12th. Okay. Tomorrow. After that, a easy part will be started.
Calculations all are very large. Yes, previous week. Sir,
I,
in my
mhm.
question, the 4 and 5 still
Yeah,
now.
actually, I already tell the support team. They will update that in the later. Okay, when
Okay,
your score will be calculated, they will before that one they will basically recheck all the particularly. Okay, I already filled the form and tell them to update the question 4 and 5 answer.
okay. And sir, today the date was released for lab exam.
Hmm.
That is Jan from first lot Jan 2 to 5.
Yeah, two to
How
five and
many days?
second.
Yeah. How many days we have to give
Basically, two
exam?
days left.
Yeah.
Okay, 2 to 5 we have a analog lab is 3 and 4 or 4 and 5. Okay, like for
Okay.
example, some student will be coming on third, so they will allot it because according to the lab combination, you are not taking the single lab, na? So maybe you are taking the two labs. So some
Okay.
student will be giving the third and fourth, some student will be giving the fourth and fifth analog lab.
Okay.
Third, they will be available in DSD lab, okay, and those fourth, five, they will be available analog lab. some student third and fourth they will be in an analog lab, and fifth they will be in embedded C or some other lab. Not embedded C, any lab, sensor lab, like for example.
Okay, okay.
So in that way they will manage make a group, because we have to at a time we are generally consider that not more than 30 students will be in a single lab.
Okay.
So that's why. But the
Sir, I
analog
have
lab is third, fourth, and fourth, fifth.
third, fourth, and fourth, fifth.
Ah.
I have only taken analog lab. Then
So either it will be third, fourth, or fourth, fifth. According to they will give you the slot.
okay,
Okay.
okay, okay. That will be. We will get that date later.
Yeah, yeah. They will basically first of all how many students will be doing that one, how many students will be attending which lab. Okay, on the basis of they will give you.
Okay, okay. I am asking because I will.
Either it will be third, fourth, or it will be fourth, fifth.
Okay, okay, okay. Okay, sir.
If you fill the first slot, second slot is I think 10th, 11th, or 11th, 12th. Like that, same way.
Huh. Okay, sir.
Okay, any other point, any other topic? Roma?
And in lab 3, experiment 3, uh, uh, we have no speaker there. Then
Yeah, then you can use the register. I already tell them, analog lab.
yes, sir.
G space group. You can use
Yes.
the register only.
Okay.
Okay. When you are coming here, so we will provide you the speaker. You can connect and check the output of
Okay,
experiment.
sir. Okay.
Sir, can I ask a doubt regarding week 4 of analog lab, sir?
Yeah, ask me.
Sir, so basically I'm getting a clipped output for I'm getting a clipped output, sir.
Clipped output after H bridge.
No, sir, week 4, sir, not H bridge, week 4.
Week 4 is the H bridge part, no, or what?
No,
Just
week
tell
4
me.
is the band pass filter, sir.
Okay, week 4 is the band pass filter.
Yes, sir. So
Uh,
basically, the output which I'm getting, it is getting clipped.
Clipped,
Like,
how much it will be clipped? What is the voltage that will be? Having?
it is going from 1 second, sir. I'll just check it. 1 second, sir. Like we are asked to test for two frequencies, 150 and one around
625, 625 around.
625, sir.
156 and
So
625, yeah.
so for that 150 voltage, it is getting clipped, sir. Like
How
if
much? How much? How much?
like I'll just show you the output, sir, because I'm not able to clearly.
Okay, the thing is that we have designed two different circuits.
Yes, sir.
That is the two different band pass filter.
Yes, sir.
Okay, if we are providing the 156 hertz frequency,
Yes, sir.
so one particularly band pass filter pass that frequency, and second filter stop that frequency.
Yes, sir. Like
Why? Because first filter will be designed on 156, second will be designed on 625.
yes, sir.
Okay, so we are getting a correct output after close first, and for the second we are getting a minimum output.
Yes, sir.
Okay, if we apply a 625, in that scenario first output will be clipped. Why? Because that will be configured at 156,
Yes,
and
sir.
we apply the 625, so first output will be suppressed, and second output you are getting a same output voltage, higher output voltage.
That is that like the DC average I'm getting as 2.5, sir.
Yeah, 2.5. Okay, fine.
But like it is coming as a not like a sine wave, like a square wave I'm getting.
Can you check the other basically you designed two different filters, na?
Yes, sir.
So check with the other filter.
Okay, sir.
Maybe possible the first filter you are checking at a 625 hertz filter. So that's why you are getting a clip output.
Okay, sir. I'll just check with
Okay.
mine, sir.
The thing is that, like for example, if I tell you they have two different circuits, two different filter. One is filter is this one, okay, that will be designed at 156.5 hertz, and second will be 625 hertz. Okay, like for example, okay, you are giving the input signal. The input signal will be go to there, two filters, and after that it will be combined. Okay, this is your circuit. If you design a 156 hertz frequency, what happen? The signal will be go 156 hertz. The signal will be go 156 hertz. Okay, here you are getting the same signal. Why? Because for the pass band, it will be providing a minimum attenuation, but here you are getting a less. Okay.
Sure, like yes, sir. Because like I have used different capacitors and resistors, so the sine wave will look like a square wave. Is that fine?
Uh,
Like
sine wave looks like the square wave.
not like square wave. They like the
Here,
like that part. It is
input
going
or output? You are asking input or
output, sir.
output?
Output.
Just change the frequencies, change the particularly resistor and capacitor, because
Ah,
that will be accurately sinusoidal signal. The
the
square wave,
output.
why you are getting the square wave? Because like for example, you are getting this is my sinusoidal signal. Okay.
Yes, sir.
Now if you clip that signal like this one, okay, if I clip the signal from here and here, so you are getting a signal like that way.
Like that, sir. The upper part, yes, sir. Same, like the green which I have drawn in blue, sir.
Yeah, because that part is clipped,
Like yes, sir.
because of you are not choosing a appropriate value of resistance and capacitor.
Like that is for when hands on, sir. In LT space, I'm getting proper sinusoidal waves, sir.
Mhm. With the
Like
breadboard.
in the breadboard, the clipped one is coming, sir.
So what particular resistor and capacitor you are using?
I am
Just
using
change a little bit value. I am not asking the value. Just change a little bit value and check if you are getting any particularly variation is that or not.
okay, sir. Like
Okay.
for the 625 hertz, I'm getting the exact output as the input.
Mhm.
Like
Mhm.
when I'm giving the 625 frequency, I'm getting
Mhm.
output also 625.
Yeah.
For 156, it's getting clipped.
Yeah, because the thing is that your frequency is very less. Okay. So
Hmm.
that means your resistance RC circuit will be should be accurately.
Okay, sir.
Okay, if you are taking a 1 kilo ohm resistance, so it will be providing you up to the 900 because it is a 10% variation.
Yes, sir.
Okay, so 10% is basically 100, so 900 to 1100.
Yes, sir.
Okay, so what is going is happening, if you change this one in the resistance value, automatically it will be clipped. Why? Because it is a RC circuit.
Okay.
Okay,
Okay.
so
Okay.
just change a little bit value of the resistor or capacitor.
Okay, sir.
Okay, and check if you are getting any variation or not.
Okay, sir.
So in that way, you just understand what is the use of these components.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Yeah. Anything else?
Sir, those who are checking the lab, will they comment anything? Any how the experiment,
They will
how the
comment in a sheet, but that sheet will be is with me. Okay, and that particularly they are commenting in the last.
okay, sir.
Okay.
Okay. We will continue send the video.
Yeah.
We
Sure.
will to the last we will know
Yeah.
what.
You
Oh,
have to send
okay.
a 3 files: LT files, document file, and video.
Okay, sir.
Okay.
Yes. Okay.
Anything else? So I think we stop here.
Thank
Yes,
you.
sir. No doubt.
Thank
Okay,
you.
sir. Thank you.